So what we're going to do today is study curvature. But before we study curvature, we have to learn something about the arc length parameter. And before we do that, we've got to talk about arc length. So I need to go back, and I'm going to go over something that we went over before, and that is finding arc length. So, but we haven't done it with vector-valued functions, although we've done it with parametric equations, but not vector-valued functions. So what I'm going to do, I'm going to start off with a vector-valued function here. And so this is the vector-valued function, and here I've got f of t, g of t, and h of t. Okay, so here's my vector-valued function. And this, if you plot these vectors, if you put in your input, you get out vectors, and if you look at the terminal points of all these vectors, what you get is some curve out here in space. So what I'm going to do is just kind of draw a curve here. And what I want to do is maybe I want the length of this curve from this point, from t equals whatever this is, to t equals this over here. In other words, what I want to do is I want to get the length of this curve. Now, the problem, so we've got to figure out how to do that. Now, what I might do is divide up the curve into some parts, increments. So maybe I'll call this 0.1 on that curve, and maybe I'll call this 0.2, and then over here maybe I have 0.3, and then maybe 0.4 over here. So, you know, I'll divide it up into 4 parts like that. And let's suppose that to go from 0.1 to 0.2, from 0.2 to 0.3, and 0.3 to 0.4, let's suppose it's all the same delta t, just for simplicity's sake. You don't have to do that, but just for simplicity's sake, let's do that. Now, what I want to do, I want to take this first little part here. I want to talk about this arc length. And then I'm going to see if maybe I can make a generalization. If I talk about that arc length, I really don't know how to do that yet. I mean, that's the whole purpose for drawing these straight lines. However, I do know how to get the distance from 0.1 to 0.2. I know how to do that because that's just the distance formula. So here's what I'm going to do. I'm going to say the distance is going to be the square root of, now notice I'm going to take the difference of the x's, so let me do it this way. I'll say f of 2 minus f of t1, right, like that. In other words, I'm using the distance formula, right? I'm going to take the difference of the x's squared, the difference of the y squared, the difference of the z's squared. So I'll do all that business, and I'll do that for each one of these. Now let me know if there's something that I'm doing that you disagree with, so maybe we can talk it through. You know, there we go. So that is definitely the distance from 0.1 to 0.2. We know that. There's no question about that. Now, let's suppose, let's hearken back to the mean value theorem. Remember the mean value theorem. Now, the mean value theorem says that if you have a curve that's continuous on a closed interval, differentiable on an open interval, then within that interval, that open interval, within that interval is some number that if you take the derivative and evaluate it at that number, in other words, remember it says this. For example, let's take this first one. Let's just look at this part right here. It says this, that between t1 and t2, there's some c1 in there such that this is true. F prime of c1, I'll call it that, is equal to f of t2 minus f of t1 all over delta t. Isn't that right? Do y'all remember that? This is the mean value theorem, okay? And we know that that number right there exists, definitely. Well, let me just multiply this delta t over, and I get f prime of c1 delta t. Well, that means that I can replace the f of 2 minus f of t1, f of t2 minus f of t1 with f prime of c1 delta t. Now, similarly, I can do this and this the same way, right? So we're ready to observe a little coolness here. I'm going to write this way. I'm going to write this as f prime, whoops, let me do this, c1 delta t, we'll square that bad boy, plus g prime c2, not necessarily the same constant, and then h prime c3 delta t. Okay, now, of course, remember delta t is positive. So that means I know I can take the square root of delta t squared and just get delta t. I don't have to do the absolute value. So let's see what happens. If I factor out the delta t squared, here's what I get. I get the square root of f prime c1 squared plus f prime c2, oh, g prime, sorry about that, g prime c2 squared plus h prime c3 squared. And then delta t over here, right? Okay. Now, what this is then, what I'm saying is, I'm saying that's the length from P1 to P2, which is not exactly what I want. I want the arc length, but I'm using that as an estimate. Now, we play the same game where we say, well, let these P1 and P2 get infinitely close together, and then we're dealing with this infinitesimal little line right here, and that's a pretty good estimate for that arc length. Well, if we let it go to 0, if we let the delta t go to 0, and we do that for every point on this curve, right? So what we have, let's just suppose that we add up all of these things, and we let delta t go to 0. Well, I'm being extremely, you could be more rigorous with how I'm writing this, but we know that if you add up all of these little lines, right? If you add up all of these and let there be infinitely many of them, really what you have here is you have the interval, and I'm gonna say from 0 to whatever it is over there, let's just go from A to B. Let's go from A to B. Okay. The arc length from A to B is just going to be this: f prime of x squared plus g prime of x squared plus h prime of x squared, right? dx. Okay. Now you notice I put an x in there. Maybe since we're using t, I should have done that. So let me just do a t. We've been using t, so let me do that. Okay, t, 1 to t. There we go. Okay, how does that grab you? This is how we calculate arc length, right? So if you give me something and you give me a starting point and a finishing point, I can tell you the arc length if I have the vector valued function. Okay? Now, so this is something that we've done before. Are there any questions about that? This is our formula. Okay, now, here's what I want to do. I want to kind of use this to transition into this discussion. And now let me see what slides I've got here. The arc length parameter. Yeah, let's just go over there, arc length parameter. Now, let's suppose that we've got a curve, and here this curve is. And I'm going to start here at 0. Okay? And this curve, let's say, is generated by r prime of t, let's say. Okay? This curve is generated by r prime of t. Now, let's think about if I tell you that if I tell you that you've traversed a given amount of arc, can you find the point on that arc easily? In other words, if I say, okay, a particle has traveled on this curve, this space curve, for 10 centimeters. I just give you that. I say, okay, it's traveled for 10 centimeters. The question is, can you find the precise point on this arc with this easily? Now, because this parameter is in t, right? And usually we think of that as time. But if I tell you that it's traversed 10 centimeters, you don't really know precisely where that is on the arc. Well, that's a problem, right? And the way we usually have these vector valued functions up to this point is we have this t as the parameter. Well, what we would like to do is you tell me the amount of arc that's been transversed or traveled across. I guess I'm using the word correctly. I can put it in that vector valued function and tell you precisely where it is on the curve. That's what I would like. That's why we're going to convert the parameter to an arc length parameter. Okay? We want to convert to an arc length parameter. That's what we want. Now, so what I want to do is show you first of all how we're going to do that, and then later I'm going to point out how that's what we're doing, but that's kind of hard. Let's look for some shortcuts. Let's look for a workaround where we don't have to do this every time. But I have to define curvature, and I define curvature with an arc length parameter. So let's see here. Let me insert maybe a first quadrant. Here's a first quad 1. Yeah, there it goes. Okay, and as usual, it's tremendous. Here, let me pause the video while I. Okay, now, so what I want to do is I want to convert. First of all, I want to parameterize a curve. Then I'm going to convert it to an arc length parameter. That's what I want to do. I want to do those two things. So let's just take something that's going to be fairly easy. Let's see here. I got 1, 2, 3, 4, and then 3 right there. Okay? Okay. 1, 2, 3, and 1, 2, 3, 4. That's a line, of course. And what I want to do is I want to come up with a parameterization for that. Now remember, there's infinitely many of them. You could just, with rectangular coordinates, find the equation for that line, and then let x be t, and then y be the equation. I want to do it a little different, just so that we'll get practice the other way. Here's what we've got. So I've got a vector valued function here. I'm going to have the parameter to be t. And here's what's going to happen. When I'm going to look at the x, and here's what's going to happen. When t is equal to 0, I want the x to be 0. Okay? I want x to be 0. When t is equal to 0, I want x to be 0. And I want y to be 4, right? Now, when t is equal to 1, I want x to be 3 and y to be 0. That's what I want. Now, I don't have to do it this way. I'm having the line, it's going to be traced out from left to right. I could have it traced from right to left. It doesn't matter. Because what we're going to do is not dependent upon that. Okay, so what would you say here? I could say, okay, let's see here. For the x, I guess I'm going to start it off at maybe 3t. Would that work? For x, because when t is 0, x is 0. That certainly works. Now for the y, I'm going to do this. I'm going to say, well, when t is 0, I want it to be 3 or 4. Okay, so I could say 4. And then when t is 1, I want it to be 0. So let me just do 4 minus 4t. That definitely works, doesn't it? That rascal right there will give you that line. Okay. Now, here's what I want to do. Here's the way we're going to work with finding the arc length parameter. Let me go back up here. what we do, we're going to start at 0, and we want a function so that as we travel along here, we will know how much arc we've traversed. And the starting point is going to be 0 for arc length parameter. And you give me an arc length. So that S value is going to start off at 0, and it's going to go until we can say, okay, S is 3 or something. And that's how long the arc is. That's what we want to do. So I'm trying to convert this. Now, one of the things I want to draw your attention to at this point is this. I don't know if this was very familiar. Did this ring a bell? Does this look like anything to you guys? This part right here, the square root of f prime squared plus g prime squared plus h prime squared. Yeah, that's right. That is definitely the magnitude. So if you have this, if you have the magnitude of r of t, if you want that magnitude, it's going to be this, isn't it? It's going to be this exact same thing. It's going to be the x component squared plus the prime, the y component squared, the z component. Right? That is the magnitude. Okay. Well, I'm sorry. I'm sorry. R prime. R prime. Sorry about that. R prime. Okay. That's the magnitude of R prime, right? Definitely. Now let's so let's go back here up here and look at this. And so it looks like when we get this magnitude, we're getting the magnitude, or when we get the arc length, it has something to do with R prime, the magnitude of R prime. But anyway, let's look at this. And so I'm going to go through here. So we just make that connection, right? So this is 3, and this is -4. Okay? Now, here's what I want to do with this. I want to get the magnitude of this. Okay, so here's what I'm going to do. I'm going to put an integral, and I'm trying to get an arc length parameter. So here's what I'm going to do. I'm going to say, okay, I'm going to call this arc length parameter S. I'm going to start at 0, and I'm going to go to t like this. Okay, that's what I'm going to do, from 0 to t. And here's what I'm going to do. I'm going to put in this thing, 3 squared plus -4 squared. And let me do du. Since I've got a t up here, I'm just going to use a dummy variable. Okay. Any questions about that? Okay. Now, let's see what this is going to be. So now we have S is equal to 5 du, and this is going from 0 to t. Okay. Because this is the square root of 25, which 5 is 5. Okay, so there we have that. Now, I know how to integrate that. Now, at this point, you're saying this is how we find the arc length parameter. And you can see I'm having to integrate this 5. So that's super easy. You can see how this could get complicated, right? Trying to find an arc length parameter. So we want ways where we don't always have to do that. But anyway, here's what we have now. We have S is equal to 5t. S is equal to 5t. Let me make this S a little more distinct from the 5. There, S is equal to 5t. So dig this now. Look at this. T is equal to S divided by 5. So now we can find a way. This is the way we can change from t to the arc length parameter, because S is definitely the arc length. You give me an arc length, I just plug it in there. That's the relationship here. So now let's see what we've got now. Now, in terms of S, we have this vector. And this vector is, let's see, it was 3t. Now it's 3 times s over 5. Okay. It was 4 minus 4t, and now it's 4 minus 4 times s over 5. So what we've just done there is we've changed the parameter. Now we have the arc length parameter. Okay. Okay. Does everybody see that? Any questions? Okay. Now I'm going to do this for a circle. Okay. I'm going to go ahead and find an arc length parameter for a circle. Now we know a circle goes like this. It goes r cosine. This is one parameterization for a circle, and then r sine theta. So let's suppose that we've got that. Okay. I haven't done this in a while, so watch out for me to make a mistake here. That's right, exactly. You're thinking ahead, right? Yeah, r theta. So the arc length, you're saying it's r theta, right? I mean, I'm saying, okay, that's where you were jumping in here. That's right. If you want the arc length, if you give me the theta, and I want to talk about the arc length, it's r theta, right? Okay. So here we have s is equal to r theta. Oh yeah, r of theta. Oh, that's what you're saying. That's what you're saying. Well, that works out though, because the arc length is r theta, right? Okay. Now let's do this. So that was quite a coincidence, right? Because you were correcting me on this, and it works out. Okay. Okay. Now look. We know this relationship, and if you don't see that, I can go back in a minute. Just ask me, and I'll show you where this comes from. But I'm assuming this is something that we all realize. Now, I'm going to solve this for theta, because right now the parameter is theta, but if I divide, I get s over r. And now I have a new parameterization for this here circle, and this is going to be r of s, and it's going to be, instead of theta, well, I have r, and here I have cosine s over r, and then sine, well, r sine s over r. There. So there we have changed the parameterization of the circle. Yes, ma'am. Where? Yeah. So what we did was r was the parameter was theta. So what we said was, well, what does that have to do with the arc length? Well, there's the relationship, and then we plugged in there. Okay. Now here is the arc length parameter. Here it is. It goes like this. The arc length parameter s is going to be this. It's going to go from 0 to t, and it's going to be, it's going to be the magnitude of r prime of u du. Okay? Do y'all see that? That's how we define the arc length parameter. Okay? Any questions about that? I mean, you can go back and look and see, okay, I see where we get all that. And I have to use the u because of the dummy variable. You know, I've got a t up here. So you don't want a t in here and a t up there. Okay. Now, something we want to take note of, very important, is this, the derivative. Let me do the derivative here. The derivative, ds dt, is going to be r prime of t like that. Do y'all see that? All I did was I differentiated this. This means putting the t in here. Fundamental theorem of calculus, right? This is exceedingly important concept. We're going to refer to it over and over again. Okay. Any questions about that? Okay. Now, okay, so we're going to move on from there and talk about curvature. Now, curvature is what we're going to use to talk about how something, to kind of describe how something curves through space. So we've got this this curve out here in space, and we want to talk about, well, how do I describe how much it curves? And it doesn't have to be a curve in space. But we're going to talk about curvature, and I want to first of all kind of give you an idea about our intuitive idea about curvature, and then I'll define it fully. Now, let's suppose we have this, well, let's say we have this real curvy part, and then kind of a part that levels off over here. Okay. Now, notice that if I put a vector in here, let me just put a couple of vectors. Let me put a vector. Whoops. Let me put a vector here and a vector here. Now, one of the things that might, and these are tangent vectors, by the way. I realize those probably don't look like tangent vectors. Let me make them look like tangent vectors. Okay, now, what we want to do with this might help you to visualize. Pretend these are the unit tangent vectors. And think about an angle made with the horizon here, or the horizontal, not the horizon, but the horizontal. Think about the vector, the angle that this first vector, let me call it T1. Let's think about the angle that vector makes with the horizontal. And let's also think about the angle that this here vector, I'll call it T2. Now, there's quite a bit of change there, right? You can see that there's quite a bit of change from this first theta, which is theta 1, and this theta is theta 2. Now, that's what we want to describe, the kind of change that's taking place in these vectors. Now, if you look at a place where it's flatter, like down here, if you look at this, there's a tangent vector, and then you look at here, here's a tangent vector. There's not quite as much change there, right? Because the curve is not moving, it's not having as abrupt, it's not having wild changes, or it's not being curvy, right? So we would say, okay, this has less curvature than this. So this right here has less curvature and this than this. Okay. Any questions about that? Now, I think your book, Zwikowski, it will define curvature. It will use a K, and it will be the magnitude of the change in that angle with respect to arc length. Now, this is and this makes sense because you're talking about how this theta changes, right? Because, I think you can get a pretty good intuitive idea about curvature from that. Okay? Now, this is not primarily how we're going to look upon curvature. We're going to look at a different definition. The definition we're going to look at, because by using this definition, we can do more with it. And remember, I said we want to get past using this arc length parameter so much. I'm going to define curvature this way. It's the magnitude of the unit tangent vector, the derivative of the unit tangent vector with respect to arc length, the magnitude of that. So it's the change of the unit tangent vector with respect to arc length. This right here is how I'm going to define curvature. And this is the definition that we're going to be using Although this one up here, I mean, they're both, like I say, depending on which textbook you look in, they might have one or both. But this right here, I mean, this one, they probably would all have this one, actually. Okay. Now, this is how we define curvature, pure and simple. Now, so you realize that, so let's just see if we can find curvature, okay? So let's go back. Now, remember, we have to have it with the arc length parameterization, right? Now, remember, a minute ago, we had this lovely circle. And we said it was the arc length was this, right? Was it R over S? Or S over R, wasn't it? Do y'all remember? Yeah, it was S over R. Look at that. Okay, now, what we're going to do is we're going to find curvature of this circle. That's what we're going to do. Okay, so I have parameterized this circle, and it says plainly that curvature is the derivative of the unit tangent vector with respect to arc length. Okay, so what I've got to do is I have to find the unit tangent vector. So here I go. I'm going to do this. The unit tangent vector is going to be, remember what you have to do is you have to find the derivative and then divide by the magnitude of the derivative, right? Okay, so here I go. Up top, I'm going to have, what is this going to be? This is going to be, what is going to be the derivative of this with respect to S? Negative R sine S over R times 1 over R, right? I can't forget the chain rule, so I've got to differentiate the inside. Okay? S, 1 over R times S is just 1 over R. Same thing over here. I've got R cosine S over R, and this is 1 over R. Okay, now, there's the derivative. Now I've got to divide by the magnitude of the derivative. Now, look at this. These R's cancel, thankfully, right? So what is the magnitude of this bad boy? Is it just 1? Yeah, okay, it's just 1. Now, okay, so we've got this. Now, this right here, and by the way, this is, okay, so here's what we've got. We've got negative sine S over R cosine S over R. Okay, so there's the unit tangent vector. Now, what I've got to do is I've got to differentiate that with respect to S and take the magnitude. Okay? Because what I'm doing is I'm just going right back to this definition. Okay? That's all I'm doing. And we're not going to be able to do this always. This is just a nice, well-behaved function here. So here we go. Here's the prime. So this is going to be negative 1 over R cosine S over R. Is that right? Okay, there we go. And then this one is going to be, what, negative 1 over R sine S over R. How'd that grab you? Everybody got that? Okay, now, one more thing, I have to get the magnitude of this. So here is my curvature. Curvature, after all that work, I'm ready to go. Now, if you look at this, well, let's just go ahead and do this. This is 1 over R squared cosine squared S over R plus 1 over R squared sine squared S over R. This is my curvature right here. Now, you'll notice that sine squared and cosine squared are there. If I factor out the 1 over R squared, I just get 1 over R. Okay, y'all see that? Any questions about that? Ah, look at this. We're saying the curvature of a circle with radius r is 1 over r. Y'all dig that? So I use this example because it helps you more to understand what we mean by curvature. Let's suppose we're walking on a circle. And let's suppose the circle has a radius of 10. Well, then the curvature is 0.1, right? Let's suppose the radius is 100. Then the curvature is 0.01, right? Okay? Let's suppose, and you see how this game is played. You know what I'm doing. 0.001, right? So what happens to curvature on a circle as the radius increases? It goes to 0, doesn't it? And that makes, intuitively, that makes sense, because if we're walking on the earth, we don't observe any curvature, right? We're just walking. In fact, there are people today that believe the earth is flat. But if we're walking on a ball, right? Yeah, we're very aware of the curvature, right? Because we're having to balance. So as the radius goes to infinity, the curvature disappears. I mean, it just goes to 0. Okay? Any questions about that? Okay. Now, what we've got to do is we've got to figure out how to find curvature. So let's do this. Let's start with the definition here. Okay. Let's start with the definition. Here we go. Now, because we can't always reparameterize a vector valued function. It's too difficult. So we want to look for properties. We want to consider this thing. And I know the magnitude is curvature, but let's just think about this. Now, let's see if we can get away from even using S at all. In other words, I want to not have to reparameterize. Well, okay, let's think about dt. Let's think about this. dt, that's something we like better. Now, I want to do this. I want to say this is dt, ds, ds, dt. Is that right, the chain rule? I can do that, right? That doesn't hurt anybody. Any questions? This is a true statement. I want to be sure I don't leave it before you understand. I'm just using chain rule. Okay, now, I'm going to rewrite this bad boy right here as t prime of t. And this over here, I'm going to write as dt, just putting in this step. Okay, y'all see that? I didn't break any civil or federal laws in doing that. Now, here's what I want to do. I want to divide both sides by ds dt. That's what I'm going to do. So I'm going to get prime ds dt down here. And over here, I get, look at that. Crap. We're almost there. We're almost where we need to be, because look at what I've done here. But you might say, there's still the s. Well, remember what the ds dt is. That's the magnitude of r prime of t, right? Isn't that what that is? I mean, we just looked at that a minute ago. So here's what we've got. We've got dt ds, which is what we don't want to work with, is equal to t prime of t over the magnitude of r prime of t, like that. So this is curvature. No reparameterization, right? Look what we've got there. That's a little better. So now we look upon curvature this way. We say, okay, I understand what curvature is. And I understand that we're working with the arc length parameter, but that's not so easy. So I'm going to work with this. This is the definition I'm going to use for curvature. That works, right? But still, T prime, that can be difficult too, right? Okay, because there's, dividing by magnitudes and all that stuff. Okay. Okay, but anyway, this is one of the formulas for curvature that you'll see as well. Okay, any questions about that? Okay. Now, let's see. Let me do this. Okay. Now, let's look at this here. Remember that. Remember this. That I keep doing the same thing. Okay. Let's think about this thing. So what I'm going to do is I'm going to get us a formula that maybe we can deal with a little more easily than even that one. We know that this one right here, this is r prime of t over the magnitude of r prime of t, right? That's the, by definition, the unit tangent vector. That's what that is. Okay, now, that's my starting point. Now, from there, I'm going to multiply both sides by this magnitude of r prime, and I'm going to get that r prime of t is equal to the magnitude of r prime of t times this. Right? That's true. Okay, any questions about that? Now, and actually, I'm going to do one more thing with this. I'm going to put this here in the middle. We will remember this. This also right here, isn't this ds dt? I think that's what that is, isn't it? Okay, because this ds dt, that's that. Now, part of the reason I'm going through this in Cal 3, because it's really in Cal 3 where you start to you're kind of transitioning over to just say, okay, where does this stuff come from? We start with the definition, and then we go through and we get all these crazy formulas. And then I guess in physics, they'll show you how to use them more for their particular problems. But does everyone see how I got that? Now, I want to do something else. I'm just playing around here. I'm going to do this. I'm going to say, just for fun, pure fun, I want to find r double prime. Okay, so what I'm trying to do is I'm trying to derive a formula for you, and I know where I'm going, but you may be thinking, he's just up there crazy. But let's get the second derivative. Well, the second derivative, I'm going to go ahead and differentiate the first. And this is with respect to t. Okay, so I took the derivative of the first times the second plus the derivative of the second times the first. Okay, how does that grab you? Everybody see that? Okay, so there's my second derivative. Now, notice I've got r prime and I've got r double prime. Those are the two things. Okay, now, here's what I want to do. I want to do a cross product. And this really, this is where I was headed. Because we're going to notice something interesting about a cross product of these two vectors, r prime and r double prime. And here we go. Now, r prime, and also, this kind of helps you to see how we use these, the properties of cross product by seeing it derived here. Okay, so here we go. I'm going to cross product. So I've got ds dt t crossed with this long thing here, right? And this looks like a bear. Looks like it's going to be difficult for us to deal with. There, look at that. Okay, so I wrote it out. Got the easy part done. Now I'm going to use a couple of properties of cross product here. I'm just going to kind of combine them. And I'm going to rewrite this way. So I've got r prime cross r double prime. Let me just do some shortcuts here. Now, I'm going to do this. I'm going to say ds dt times second derivative times the cross product of the t's, right? See, I've done that. I'm kind of distributing and then factoring out the constant. And then plus over here, ds dt squared times t cross t prime. Okay, how does that grab you? I just use properties of cross product. Okay, everybody see that? Okay. Bear with me. We're about done. And it's going to be a very, very neat, elegant little thing we're going to see. And then we'll do one more thing, and then we'll be done. Okay. Do you see anything there that I can just sort of get rid of? Yeah, that's 0. Thank goodness, right? We never liked, we didn't want to have to deal with that. So now we've got this. We've got r prime cross r double prime. And then we still got this. Now I think what I'm going to do is go ahead and let me do this. At this point, let me just go ahead and do the magnitude here. I'm going to throw a magnitude. I'm going to take the magnitude on both sides. And of course, this is just going to be itself, right? But I'm going to do this. I'm going to change it to the magnitude of r prime of t squared, right? Because ds dt is r prime of t magnitude. Now this thing, t cross t prime, well, and I'm going to show you where I get this, but this is t, the magnitude of t, times the magnitude of t prime. Now, I'll show you where I get that. Remember we said this. We said that if you have vectors, alpha cross beta, and you want the magnitude, that is going to be the same as the magnitude of alpha, magnitude of beta, times sine of theta. Well, we know that t and t prime, they are orthogonal, right? So theta is 90 degrees. So sine is 1. So really, our alpha is t and our beta is t prime. Y'all see that? So this is where I get, this is why I had the gall to rewrite this as this. Okay, now let's see what we've got here. We've got a beautiful thing here. We've got the magnitude. Okay, now the magnitude of t is 1, right? So this thing simplifies a little bit right away. Okay, does everybody see that, how I got that far? Well, it's a unit vector by definition. Now, let's take a look at this bad boy right here. Remember we said this. I think we said that the magnitude of t over, what did we say the magnitude of t? Didn't we say that was curvature? That was one of our definitions for curvature, right? Well, look at this. The magnitude of t prime, the magnitude of t prime. Let me just replace the magnitude of t prime with k times this thing. In other words, let me just multiply it through by that denominator. And then I get this. I get this. Well, just the magnitude of, okay, right? Look at this. Look. We got K in there. So look at this. We've got another formula for curvature that might be a little bit easier for us to deal with. We've got the magnitude cross the second derivative, right? The magnitude of this cross product divided by the magnitude of R of t cubed. There it is, another formula for curvature. Okay? How does that grab you? So we've got a couple of formulas for curvature that we can really use. Okay? Now, you got to admit that's pretty slick. So we've got another formula for curvature here. Any questions about that? Okay. Now, and really, when it comes to finding curvature, it's going to be a matter of, using one of these formulas. Okay. Now, we've been talking about curvature, though, for for curves that are generated by vector-valued function. And here, here you have you talk about a cross product. That's vectors in space, right? So you have three, the x, y, and the z. So we get a cross product. But let's suppose we have a curve that's not defined with a vector-valued function. Let's suppose that we have this curve, y equals f of x. Let's just suppose we have that. And we want to talk about the curvature for that thing. Well, we know how to find the curvature for a vector-valued function. We definitely know how to do that. So let's just make this a vector-valued function. Let's say this is going to be x, f of x, and let's put a 0 over here. Okay? So we're saying it's a vector-valued function. The z component is always 0. Now, what I want to do, I want to use this previous thing, this right here, which of all the stuff I'm saying, it kind of boils down to, yeah, you're going to have to use this formula right here, and this formula that I'm about to show you. That's mainly what you're going to be using. But here we go. So let me use that formula. We have r prime of x, which is 1 f prime of x, 0, right? And let's find the double prime. Okay, there's the double prime. Okay. Now we want to cross product those, right? That's the international symbol for cross product. Okay, that's what we want to do. We want to cross product, and then we're going to divide by the magnitude. So here we go. Here's the cross product. Almost done. Got to get another formula here. Every time I give you a new formula, it's awesome because you know that it's going to be easier on you. Okay, so there's that. Now let's go through the process here, cross product. If you look at this, everything's going to be 0 except the very last thing, right? This right here is just going to be f double prime. That's what that's going to be. If you get the cross product, I mean, because you can see all those zeros, and it doesn't take much imagination or working ahead to see. Yeah, the only thing that's going to matter is this. When I multiply 1 times f double prime. So if we talk about the magnitude of this, then we're going to get, let me just call it, well, I'll just call it double prime here. Yeah, there's the mag. Yeah, well, it's just going to be the absolute value, isn't it? I started to, yeah, it's the absolute value. Okay. Right, because we square it and take the square root. So it's the absolute value. Okay. Any questions about that? Now, one more thing I want to do. Remember we said this right here, this was R1. We got to get the bottom because we've got the top of this right here. Now I got to get the bottom. So what I'm going to do is I'm going to say, okay, R of t, or R of x it was. Let me just do R prime. R prime was equal to, what was it? Was it 1, f prime, and 0? Now let's get the magnitude of that. So here goes the magnitude. Isn't it 1 plus f prime squared, right? So whenever you have a scalar function in the 2 dimensions and you want to get curvature, you put these things together. Curvature is equal to the absolute value of whatever the function is, right? Second derivative, all over. Now, this is the square root of 1 plus f prime squared. But remember, it was cubed here, right? So it's the square root of 1 plus f prime, the square root of that, all raised to the 3rd power. Okay? So here we go. This is going to be 1 plus f prime of whatever. I'll just put f prime. F prime squared to the, what was it, 3/2? There it is. So that's another formula for curvature. Curvature. Okay, any questions about that? Okay. Now, I should creolicize that. Okay, there it goes. Now, one of the things about I just want to mention one more thing to you about curvature. Now, next time we'll do some practice. I'll have to look at the calendar and see what's ahead. But if you look at something like this, and we want to find the curvature. Let's just find the curvature here. And I want to, so this will be a practice using our formula. Remember, we got to find the second derivative, right? So here's the first derivative. The first derivative is going to be 1 minus 1/2 x, right? And what about the second derivative? Second derivative, is that just negative 1/2? Okay, negative 1/2. I think I did that right. Now, now if we want to talk about the bottom, so the top, the magnitude, or this thing right here, this is just going to be 1/2, right? Now, I want to do the bottom now, because we're trying to get the curvature. I need the absolute value of the second derivative, which is that. Now, let's look at the bottom. The bottom is, what was it, 1 plus, and it was this thing squared. And it was to the 3/2. So let me just do that to the 3/2. This is what we had, right? Now, if you look at this, this is going to be 1 plus. If I square that out, that's going to be 1 minus, that's 1, right? Is it like that? Did I get that right? I squared the first 2 times this, and this is an x, isn't it? X. So 2 times the, and this is x squared. Okay, gotcha. Now, is that right? I've got the first thing squared, 2 times the product. The product is negative 1/2, so 2 times that's 1. And then, so I think that's it, right? This is the bottom. So let's see what this looks like. This is going to be 2 minus x plus 1/4 x squared. Okay, 3/2. Now, here's what I want to do. I want to find the curvature at 2. Let's suppose I want to find the curvature at 2. Okay? So here's what we have. We have this formula. Now, the second derivative was just 1/2. So here's curvature. It was 1/2, and on the bottom we had 2 minus x minus 1/4 x squared to the 3/2. So what I want to do is I want to find curvature at x equals 2. Okay, so here we go. At x equals 2, we get 1/2, and dig what happens down here. We have 2 minus 2 minus 1. Is that right? It was plus, oh yeah, plus 1/4. Okay, and that's 3/2. So it looks like the curvature is 1/2, right? Do y'all see that? Any questions about that? Okay, so that's the curvature is 1/2. Now, let me go back up here. This would be the grand finale. Let me do this. I want to show you something about curvature. Let me do this. I want to make a circle here. Okay. Actually, let me do this. Hang on. I messed up. I'm trying to make a circle here. Okay. This is a circle, and what I've done is I've made the circle where it's just tangent to the curve up here. Okay? And what you notice is the radius of that circle is 2. Okay? Now remember, we said for a circle the curvature is 1 over r. And if the radius here is 2, that would be 1 over 2, right? So it would be 1/2. So you get the same curvature. In other words, this is a way to kind of help you visualize. When we talk about curvature, you can think about putting a circle that's tangent at a point there and looking at the radius. 1 over that radius is your curvature. Okay? Any questions? All right. Okay. Ollie,